Okay, on this video, we're going to finish up the notes for the product and quotient rules. So we talked about product and quotient in class. We each taught it to a partner of ours, but we're going to do that last page. So we're going to go to page 52 because we didn't cover that. So what we're going to talk about today is kind of using a table to find a derivative value, to find the slope at a specific point. Okay, so what does that look like in table form? Okay, so go to page 52. So we have differentiable functions, and that just means our derivative exists, f and g, and they're defined for all real numbers of x. Values of f, f prime, g, and g prime for various values of x are given in the table below. So this table that we have here underneath the top of the page is giving us values for f, f prime, the derivative of f, g, g prime, the derivative of g. Okay, remember our g prime and our f prime are the slope of f and g at those specific values. Okay, so I want to know if h of x is f of x divided by g of x. I want to find h prime of 3. Well, in order to find h prime of 3, the first thing I need to do is to find h prime of x. So that's kind of what I'm going to do first. Let me make that a little bit smaller. Because of the fact that I said f of x divided by g of x, that makes it a quotient. So we're going to use the quotient rule to find the derivative. That quotient rule says first we take the derivative of the top. Okay. We use f prime because we're in function notation. Times the bottom. Minus derivative of the bottom, so g prime. Derivative of g is g prime times the top. And then we're going to divide all of that by the original denominator squared. Okay, so that's kind of our derivative. Yes, it's in function notation, but it is the derivative of h. And now to find h prime of 3, all we're going to do is plug in a 3 for every x in our problem. So if there's an x, we're replacing it with a 3 for our entire equation. That was not a nice looking 3, so I'm going to rewrite it a little bit better. Okay, everywhere in the problem I'm replacing x with g, just function notation. And then this is where the table comes into play. We're looking specifically at x equals 3. So that's this value here. And what we're going to be doing is we're going to be looking at all of those values in that table to figure out what that is. Okay, so now we're just going back to that table and plugging in. So when f prime is when x is 3, our f prime function, if we look at that column right there, our f prime function is in fact 8. Okay. When x is 3, our g function, so now I'm looking in this column, is -4. Minus g prime gives us a -4. Again, I'm looking in that g prime column. And then f of 3 gives us 1. And then all of that divided by that -4 squared for g of 3. And then after this, it's just computation. So we get -32 minus a negative is going to make that plus 4 over 16. So -28 over 16, and that reduces, both of them are reducible by 4. So we're going to get -7 over 4. Okay, so the slope for h at x equals 3 is -7 over 4. The next one, we want to find the derivative of the square root of x times f of x when x is 4. Okay. So I'm just going to quickly rewrite this, and I'm going to rewrite it over the top, because remember we need that in power form in order to use the power rule. So that means our derivative of y with respect to x, dy dx. So it's a product, therefore I'm going to use my product rule. It says the derivative of the first. So x to the -1/2, just using my basic power rule like we usually do, times the second, plus derivative of the second times the first. Okay. From here, especially because we're dealing with negative exponents and rational exponents, we want to put it in that form back into the original form. That way we can plug in the 4 a little bit easier. So I'm just going to rewrite this 1 over 2. The x to the negative 1/2 is going to go to my denominator and then go back into root form. Times f of x plus f prime of x and back into square root form. And that way I can take my derivative and evaluate it at x equals 4. Remember, that's new notation for you guys. And all we're doing is we're plugging in a 4 in for the x. All of the x's in the problem. That is an ugly 4. Let me fix that. And now we're just going to do some calculations. So square root of 4 is 2, times 2 is 4, so we get a 1/4. My f of 4, now I'm going to where my x is 4 on my table. So where x is 4, we're going to use that line right there for this problem. So we're going to use that for this. So if I look at f, now I'm looking at, let me erase that. I'm looking at this column. So when x is 4, f of x is 10. Oh, I totally forgot a piece of that problem. I'm going to come back up here really quickly. That is terrible. Excuse me. So I did miss this entire thing. I was wondering why I had so much room. Okay, so still 1/4, and then f of 4 is 10. That's exactly what I wanted. Plus f prime of 4. So now I'm looking in this column for f prime. Gives us a -1. And then times square root of 4 gives us 2. So then I'm just going to simplify this. I get 10 over 4, which reduced to 5/2, minus 2. If I get a common denominator, 5/2 minus 4/2, that gives us a positive 1/2. So even when we're in table form, we're still kind of doing the exact same process. Because we've been introduced to the quotient rule, we can actually find the derivatives of the rest of our trig functions, because every trig function can be written in terms of sine and cosine. So if I want to take the derivative of tangent, I can rewrite it in terms of sine and cosine. We know that the tangent is our sine of x over our cosine of x. And now it puts it into a quotient rule, which means we can actually use our quotient derivative rule to take the derivative. So that's exactly what I'm going to do. Okay. So it says, the quotient rule says to take the derivative of the top times the bottom. I forgot the c. Minus derivative of the bottom times the top okay, my pen is messing up today, times the top all over the bottom squared. Okay, so I'm just going to simplify this. We get cosine squared. So cosine squared x, negative and positive, or two negatives are going to make that positive, and sine squared x over cosine squared x. Okay. And if we look here, to that value right there, that happens to be one of our identities, which means we can change it to be 1 over cosine squared. So 1 over cosine squared is the reciprocal identity for secant squared. So that means the derivative of the tangent of x, in fact, is secant squared of x. And that's kind of what it says right here. Okay. So if we do the same process with cotangent, we get that the derivative of cotangent is actually negative cosecant squared of x. Okay, so the same process will work for that one. Now let's look at cosecant of x. I can rewrite cosecant. Cosecant is the reciprocal function of 1 over sine of x. Puts it into quotient form, into terms of sine, which means I can use my quotient rule to take the derivative. So I'm going to do exactly that. So the derivative says to take the derivative of the top, which is 0, times the bottom, minus derivative of the bottom, times the top, all divided by the bottom squared. So I'm going to simplify this out. 0 times sine of x gives us 0, and then negative cosine x times 1 just gives us negative cosine x. Well, and I will put a 1 in there, just for fun. Okay. And then, of course, sine squared x. Now, if we think about this, we can actually look at these as two separate fractions that are being multiplied. So I'm going to split up that sine x. Okay, so all I've done is kind of split up my fraction. Now, you might think, why are we doing this? But if we go back to what we have now, we can clearly see that this idea of negative 1 over sine of x can be rewritten as negative cosecant x. And then cosine over sine is actually cotangent x. So the derivative of cosecant x winds up being negative cosecant x times cotangent x. So it's kind of in its own derivative. And that's exactly what it says down here. We can do that exact same process to get the derivative of secant x, which happens to be secant tangent. So now you pretty much know every derivative rule with the exception of one. But this is kind of where we're going to stop for this unit. If you have any questions, come see me in the morning.